Well, I would, so I'm going to give 2 lectures here. And I would have said this in my, well, I'm going to give 2 lectures in the program. And then I'm going to give a so-called distinguished lecture next Wednesday at 4 p.m. A week from Wednesday. These will all be entirely different. We're set. Well, I'll go ahead and say that anyway, because I'm actually, according to my program, I'm starting early. Is this thing not on? All right. So I would urge you to attend all the lectures in the school. But my 3 lectures will be this one, which is kind of like a colloquium, which I thought would be appropriate for the first talk in the school. Tomorrow will be very technical. So it's the kind of thing you might get if you're sitting in a classroom hearing a lecture. And then next Wednesday, a week from Wednesday, it's a whole new world. It's the only thing I think about, and I'm very keen to communicate it to you. So I strongly urge you to come to that lecture. All right, let's get started. I always wonder with Zoom how much of the screen is going to be covered up. So this is terrific. Very little of it's covered up. So I'm going to be talking about kind of a particular history of quantum metrology. And of course, the history is entirely me because I'm giving the talk. And it's not such a bad thing to do. But you will see that as we go along. All right, now let's get started. And I have plenty of time since I was told I have an hour and 15 minutes. So these slides will come up whenever you can take a break from concentrating. And they have green borders and a photo of some place in the world that I really like. So this allows you to see places in the world that I really like. Also allows you to take a break from thinking. So those are my 2 kids, somewhat about 10 years younger than they are now. And I, of course, was scared witless because it was about, I think, 1,500 feet. That is 500 meters, at least 500 meters down to the ocean. Tremendous fjords in Iceland. All right, let's get started. The general context here is quantum information science, which is a field that sort of emerged in the last 25 years. And a kind of big picture on that is we taught the computer scientists something, although they didn't really learn it very well, that computational complexity depends on physical law. That is, what they thought was computational complexity for a computer formulated in a classical realistic world is not the whole story. And there's a totally different kind of computational complexity that applies when you can take advantage of the superpositions of quantum mechanics. So that's kind of, that's the plus for us. For us, there's also a lesson, that is physicists. I assume most of you are physicists or intend to be physicists. When I was a student, quantum mechanics was a nag. You can't do this, you can't do that, don't do this, you can't do that. And in particular, you can't measure non-computing observables simultaneously. And in the end, the uncertainty principle will always get in the way of any measurement you want to make. But quantum information science has taught us a lesson that quantum mechanics can be a liberator. And the question we now ask is not, what does, generally in quantum information science, we don't ask, what can be accomplished with quantum systems that can't be done in a classical world? So we ask that question. And we explore what quantum systems can do instead of being satisfied with what nature hands us. That is, we don't necessarily we don't necessarily deal with the kinds of designs nature has. We design our own systems that can do things that can't be done in a classical world. That's a kind of quantum engineering. So that's ultimately going to disappear from us as physicists into engineering. Quantum engineering will just become like any other kind of engineering. And all the tech companies will prefer to hire engineers to hiring physicists because engineers are far easier to herd around and get them to do what you want than physicists are. But there is one sort of exception to this rule that quantum mechanics is a liberator, and that's in metrology, which is at the heart of physics. It's taking the measure of things. A physicist tends to think that something isn't real unless we can measure it. And metrology addresses how well can we measure things. It can also be thought of as extracting information from physical systems, which of course we wouldn't know about them unless we could extract information from them. And in this case, well, we have both of these things are still with us. Quantum mechanics is a nag and quantum mechanics is a liberator. We still have this kind of battle between the two. And that's really what modern quantum metrology is about. How do we make precise quantum measurements? And what does quantum mechanics tell us about how well we can do those measurements? Are there actually limits on what we can do? So the original thing that I was taught as a student is still here in quantum metrology. That is the kind of fight between quantum mechanics as a liberator and quantum mechanics as a restriction on what we can do. This talk is going to be about the following. It's going to be about how physicists really, although we like to think ourselves as incredibly rigorous, and you know, we are. Physics is about telling stories about systems, and the stories are founded in some rigorous foundation. But to design a really good measuring device, you need to have a noise model, and you need to be able to tell a story about how that measurement model works. I'm going to tell you in the first half of this talk about a particular story of Gaussian noise and interferometers. And that's the way interferometers have now gotten to be where they are. I'll mention the incredible advance that LIGO just announced. I can't remember the dates anymore. A week ago, Friday, in Estes Park, which is in Colorado. So the first half of the talk is going to be about stories about noise, and in particular, it's going to be about noise in an interferometer, because that's both what I did and what I know about. And the kind of more modern approach in quantum metrology, which is rigorous analytic techniques for giving proofs of how well you can do under various circumstances. You should keep in mind when we talk about rigorous analytic techniques with proofs, that the purpose of a proof in physics is to identify the assumptions so you can go out there and get around them if possible. That's really the purpose of proofs in physics. Sometimes they're nearly ironclad, but often you can take a little chink out of them and look at that and say, oh, we could get around that if we changed our system a little bit. All right. So take a little break, then we're going to get started. There's the clock. So I'm set. Yeah. That's a terrific place in New Mexico. You should come see us sometime if you're in New Mexico. And I'm going to be now, although you can't go there now, the local Pueblo Native Americans who are at the entry to this shut it down at the beginning of the pandemic, and they've never been convinced to open it back up since the pandemic is over. They're not really keen to have all us guys running around on their stuff. All right. So I'm going to be talking about the application of squeezed light in optical interferometry. And this is the primary application of quantum metrology now. I'm only going to talk about a piece of that application, but all that's done in the big gravitational wave observatories, 2 in the United States and 1 in Europe. There are 2 big interferometers, one in Hanford, Washington, one in Livingston, Louisiana in the United States, and one in Italy. I mean, if you look at these, you might want to ask, which of these would you prefer to work at? Louisiana's in a swamp, Hanford's in a desert, and you know, this looks pretty nice. Anyway, so let's first of all just settle how a gravitational wave works. A gravitational wave is a kind of oscillation in space-time. So if I put 2 free masses down a certain distance apart, the gravity wave comes along. If it's a monochromatic wave, it will just change the distance between those 2 masses periodically, as shown up there. So the conventional way to designate how accurately, to designate the strength of a gravitational wave is in terms of a dimensionless parameter, h, which is called the strain. So it's the amount of motion divided by the separation between the 2 masses. So on these guys, you can see the separation in these interferometers. Basically what you're detecting is the distance, not in an absolute sense, you're detecting changes, the distance between a near mirror in a Fabry-Perot-Michelson interferometer here and a far mirror at the end of the interferometer. And we're going to see that typical sensitivities need to be about 10 to the minus 22. So 10 to the minus 22 times 4 kilometers is, oh God, help us about doing these 4 times 10 to the minus 19 meters. So that's the kind of motions they're detecting. All right. Pretty small. You tell some people that and they just say, well, that's impossible. And that's, you know, a tiny fraction of the size of the nucleus. But of course, they aren't detecting nuclei, they're detecting the motion of big mirrors. It all works. Okay. I'm going to show you here the first detection, which when they turned on LIGO for some new observing run, I believe in 2015. And then they published in 2016. They turned on the interferometers, and within a few hours, they had detected this event. And you see this event in the Hanford detector. So you see that, well, here's a kind of rendering of it with the noise removed. 2 black holes are spiraling in toward one another, and then they coalesce here, and there's a big burst of radiation. You can see this was an event at about 10 to the minus 21 at peak strain. So those were 2 big black holes, about 30 solar masses apiece, about a billion light years away. One of the incredible things about this, the energy in the gravity waves was about 3 solar masses coming out in a 10th of a second or a 100th of a second. And during the time it was on, it outshone the whole visible universe. It's pretty remarkable. Here's a question for you. So that's a pretty powerful event, right? 3 solar masses being radiated away in a 10th or a 100th of a second. If you had been in a spacecraft close to it, how far away would you have to be before you were safe from the gravity wave, ripping you apart with its tidal forces? What do you think? Anybody got a guess? Would you need to be a light year away? Would you need to, could you run right up next to it? Well, the answer is, I believe you could take a strain of 1,000th, probably even 100th. You could have your body stretched by a part in 100, or certainly a part in 1,000. You would notice it, I think, at a part in 1,000, but you certainly wouldn't be hurt by it. And for that, you need to be 1,000 Schwarzschild radii away, which for these is about the distance to the moon. So you could have been the distance to the moon away from this event, even though it was radiating more power than the whole blasted visible universe while it was on, and you would hardly even notice it. That's a kind of signal that it's gonna be hard to detect those things. It's gonna be darn hard to detect them. And that's why we need these incredibly sensitive instruments to do it. So what we had was an advanced LIGO, which was the, and I could have the lingo wrong because I don't keep up with what LIGO calls all of their AA LIGO and so on and so forth, but I think this was called advanced LIGO, and it was observing run 3, I think, maybe it was 2. No, I don't remember. Anyway, the strain sensitivity was about 10 to the minus 22. So the differential displacement sensitivity, as I said, it was about 4 times 10 to the minus 19 meters. And that was from about 50 hertz to 2000 hertz. Since then, they've improved things because they, among other things, put in the squeezing that I'm going to talk about. And now they put in an even more spectacular version of squeezing, which I will say something about. And their sensitivity is 5 to 10 times better than this. And it extends in the important thing is it extends down in the low frequency band to about 2, 10, 20 hertz. That is, they are now radiation pressure noise limited down to 10 or 20 hertz. All right. So now we've got to see if this thing is going to work. But it did, but with a considerable delay. So we need to go back to that. So how do they achieve all that? They get all the blasted light they can. They have very high power. They use Fabry-Perot-Michelson. So in the arms are Fabry-Perot cavities. So the light bounces back and forth many times or is stored for a long time, building up the signal. They use what's called recycling, both at the power and the signal end. At the power end, that means that the cavities are so good, the mirrors are so good that really, in the amount of time they store the light, which is about a millisecond or so, maybe 10 milliseconds. Amount of time they store the light, there are essentially no losses, and they could store the light for vastly longer than they do. So they let it out. And so 99% of the light, maybe more than that, comes back toward the laser. They put a mirror there and put it back in. And that jacks up the power by an enormous amount. The whole thing wouldn't work without that. There's no way it would work without power recycling. And now they put squeeze light in 2 ways, which we will talk about. And I do know there's a bunch of LIGO India people in the audience who are looking at me and wondering, do I know what I'm talking about? And if I don't, just tell me. So very quickly, we're going to scale back now from the LIGO interferometer to a simple Mach-Zehnder interferometer. And what should I tell you here? Well, the first thing is, I'm a person who, although you're not supposed to call yourself this now, I'm a sort of perfectionist following my PhD supervisor, Kip Thorne, who is definitely a perfectionist. And yet, I misspelled Zehnder for 20 years before somebody told me that I needed to put that H in there. And this is just because once you become sort of an authority on something, people are reluctant to tell you you don't know what you're doing. And so you go for years misspelling Zehnder and they don't even tell you. All right, let's look at this interferometer. So we're going to replace the gravity wave interferometer with a very simple Mach-Zehnder. Here's the laser that puts in light with a mean field A, and the quantum fluctuations are delta A. We're going to say that we're detecting a phase shift, a static phase shift. due to these pieces of glass in the arms. We'll say a little bit about what happens differently in LIGO in a minute. And we're going to ask, where's the fundamental source of noise in this interferometer? Well, this has been known for a long time, and it is a story. It is the story I'm going to tell you. It was identifying where the fundamental noise comes from that allows LIGO to engineer the noise in ways that are truly spectacular. But until that was identified, until that story was told, you didn't know what to do. So what we're about to tell you is that story. So the laser has a mean field A, and it has fluctuations delta A, and in the limit, those would be, and they typically are, very close to being vacuum noise with a highly stabilized laser. And then there's another port into the interferometer, which I'm calling B. And we're going to first assume that vacuum comes in there. And the vacuum has two so-called quadrature components, one of which, X1, is in phase with the mean field of the laser, and the other of which is out of phase, so it produces phase fluctuations. So X1 produces amplitude fluctuations once it combines with the laser light, and X2 produces phase fluctuations. All right, so let's see what happens. Here we show those fluctuations. Here's the mean field of the laser. We're not going to draw the laser's fluctuations because in a properly balanced interferometer, or the whole point of a properly balanced up interferometer is that the noise coming from the laser is totally irrelevant. It is balanced away and you don't have to worry about it. And this was a big puzzle 45 years ago, and it's not a puzzle now. But we are going to look at these fluctuations coming from here, and we have the amplitude, the stuff that's going to be in phase with A, colored blue, and the stuff that's out of phase, colored green. So now let's send those, and we'll think of those as actually mean fields. They're actually in an interferometer there with whatever bandwidth they're in. They're fluctuating, mucking around, but we don't have to worry about that. The argument we're going to make doesn't have to worry about that. So the first point is that at a beam splitter, the transformation is B gets added to A in this arm and B gets subtracted from A in that arm. And how do we know that? Well, you can just go check you need to preserve the commutation relations of these things, which are creation and annihilation operators. But there's a simpler argument. If this fluctuation increases the amplitude in this arm, then by energy conservation, it must decrease the amplitude in the other arm. And the phase fluctuations don't have such a simple energy conservation argument, but they work the same. They must work the same. So these fluctuations are now out of phase, or they're differential fluctuations between the two arms. So we can now see that, without even going any further, the green fluctuations are the whole story. Because what an interferometer will detect is the differential phase shifts between the two arms, and the green fluctuations are exactly like a differential phase shift, adding to the phase in one arm and subtracting from the other. So they are the fundamental noise. You don't even have to go any further to know they are the fundamental noise source. We'll come back to the blue fluctuations in a minute, but there we impose the signal that we want to get. And then we go through the second beam splitter. And after we go through the second beam splitter, the phase fluctuations, the green fluctuations, have become amplitude fluctuations. And why is that? That's so we can detect them. That's what an interferometer is. It is that thing that turns phase into amplitude so you can detect it. So you can see that if there was a signal from the phase, or if there is a fluctuation, there will be differential amplitude fluctuations up here. These are meant to represent photodetectors, and then we subtract the photocurrents. And as a function of phi, we'd get something like this. We choose to operate here. And what do we get? The green fluctuations cause this or a signal. So we choose to operate it at this point where nominally the two photocurrents subtract to 0. And the phase fluctuations simply move that 0 back and forth. And that produces noise that will confuse the signal. So a signal would be moving up and down this curve at this point. And you can see that these fluctuations do the same thing. So they're the fundamental noise source. And then you just go through a little diddly calculation that the uncertainty in measuring the phase is simply the uncertainty in this phase quadrature divided by the square root of n. Square root of n gets it there because the whole thing is activated by the mean field, which has, the mean field has size square root of n. All right, terrific. I do want to, so anybody got any questions about that? Because this is the story. This is the story of vacuum fluctuations from the unused port in an interferometer being the fundamental noise source in an interferometer. It is a model which elaborated to be frequency dependent, that is sidebands about the mean field. When elaborated in that way, it is still today what LIGO uses to analyze what's going on. It is a story of vacuum fluctuations on top of the mean field. It's the whole story. And you can get away with it in LIGO because the mean field is darn big. So nothing else matters. All right, now we didn't say anything about the radiation pressure fluctuations. So you can see that if we were trying to detect the motion, let's say, of these two mirrors, well then these blue fluctuations would in this rendering, they would push on this mirror and pull on that mirror and produce, and thus produce a phase shift of exactly the sort that we want to detect. So we would also find that in our interferometer, radiation pressure fluctuations were important. And the explanation for that was also given about 40 years ago. At the time, nobody really knew that LIGO would have to have so much power that radiation pressure fluctuations would be important. And nobody had ever detected the effect of radiation pressure, of the quantum version of radiation pressure noise, or anything even remotely like that. But now it's important, and so radiation pressure noise is important. So what has happened over the last 40 years is very early on, Bill Unruh understood that you could get rid of the radiation pressure noise and the shot noise. So the shot noise is the stuff due to the phase fluctuations. You could get rid of both the radiation pressure noise and the shot noise by doing squeezing that depended on the sideband frequency to the main carrier. And that was an idea that sat there for a long time because nobody had a clue how to do it, nor did they need to do it. And then along about 2000, a group of people at Caltech realized how to do the frequency dependent squeezing. Jeff Kimball was the person who figured out how to do it by processing a squeeze source through a very high finesse optical cavity. And they just did that. So a few years ago, they put squeezing, I think 2019, they put squeezing into LIGO in the way that gets rid of shot noise. And just in the last week, they announced that they put squeezing in the way that gets rid of both the radiation pressure noise and the shot noise. And so there's no limit to what they can achieve. Of course, there are limits because the thing is lossy, but they're off to a whole new world. Okay, I'm not going to talk about the radiation pressure noise. I'm just going to talk about the back action, talk about shot noise. Okay, any questions? Yeah. And somebody's probably going to have to interpret for me because I can't hear anything anymore. How is the back action distinguished from the?
Different from the radiation pressure.
It's the same thing. The back action, the radiation pressure noise is the back action. Okay, that is the way it works. All right. So now I'm going to give you a tiny history of the developments in squeezing over the last 35 years. So I like this particular graph by a German group from 1997 because they actually purposefully rigged their data to look like pictures that I drew in my 1981 paper. They look identical to those pictures. So the standard coherent state way of thinking about light, so that would be when the squeeze light's combined with the mean field in the arms. So a coherent state is represented by a mean field and and then fluctuation is represented by a circle because the amplitude and phase fluctuations are equal. And if you plot the electric field for that electromagnetic wave as a function of time, there's the mean field oscillating away, and then the fluctuations on top of it are uniform through the cycle. If I plot a squeeze state that has squeezed amplitude fluctuations, what that looks like is this. So zero crossings are blurred out. That's the fact that the phase fluctuations are bigger, but the amplitude at the peaks is better defined. Okay, and this is the case of amplitude of reduced phase fluctuations, so the zero crossings are well defined. Okay, and what these guys showed with about 3.5, a factor of 3.5 of squeezing is here's a coherent state, here's a squeezed vacuum state, here's these two. Well, no, here's a squeezed vacuum state. Here's the squeezing in the phase, and here's the squeezing in the amplitude. So their pictures they more or less look exactly like mine. They're a bit of a fake, but we won't worry about that. They're not really a fake. All right. And over time, the key thing in producing squeezing that would work in LIGO was the squeezing initially tended to be at sideband frequencies up to a megahertz. And LIGO doesn't work at a megahertz sideband. As you could see, it works at kilohertz and below sideband frequencies. And so you needed to push the squeezing down into the audio band. And that was achieved over a long period of time. This technical development took nearly 35 years. Today, so here's an example of the way things were in 2010. This is at audio frequencies. Here's the level of shot noise. Here's the squeeze noise, and there's the anti-squeeze noise. So I think they had nearly 10 dB of squeezing, as you can see. And then in 2012 or so, the LIGO put squeezing into the Hanford detector, and here's their sensitivity plot, or their noise plot. This is the shot noise regime. Down here, below a certain point, they're dominated by something else, which is now radiation pressure noise, but at that time, this was other extraneous noise. Isn't it great the way theorists can say other extraneous noise? You know, that's not fundamental, just get rid of it. And then they spend manpower for 10 years and millions of dollars getting rid of it. And the theorist just says, get rid of that extraneous noise. Not fundamental. Anyway, this was not fundamental noise at the time. All right. And these guys got a net kind of 2 dB shot noise reduction in the actual LIGO interferometer. And that was reported in 2013. They weren't actually in observing mode here, nor did they have both interferometers on. but still they were able to demonstrate the effect of using squeezing. And that is another point. They tell me now that, why do they have two detectors? Because they need to show that events in one are coincident with events in the other. But they tell me now they're so confident about the noise that in principle, they really only would need one detector. And they really know what they're doing. It's not to say they will. I mean, you guys are going to build another one here, so then they'll have three. And eventually the Europeans will have another huge gravity wave interferometer called the Einstein telescope, and that too will be another one. Yeah, there was a question over there. The what?
The short noise you had that imposed different Mach sensors, that seemed to be independent of frequency, or is it like here it seems to be linearly stable?
Yeah, that's because this has all been converted to sensitivity for H. So although the shot noise is flat, the sensitivity for H is basically at higher frequencies, you are averaging over a shorter time. So you have a smaller number of photons in your 1/square of n. So the noise goes up when translated into strain sensitivity. And at this end, the same thing is true, except there's the additional processing of the signal and the noise through the response function of the pendula, which is 1/frequency squared. And so all that goes in to make a curve that always looks like this. And somewhere along in here is where the shot noise equals the radiation pressure noise, and that's called the standard quantum limit. They didn't actually reach the standard quantum limit here because they weren't radiation pressure noise limited, but they are now. I saw some incredibly impressive pictures the other day. All right, now here we finally have LIGO, actually, LIGO and Virgo both doing stuff. So here's the Virgo data without squeezing, with squeezing. They get an improvement in sensitivity clear down to here, and that's because they're nowhere near the optimum power to reach the standard quantum limit. And LIGO, where did I put the LIGO data here? Well, maybe I didn't put it anywhere. Well, there's screw ups and everything, and anyway, that's life. All right, now I just want to show you one other way to think about squeezing and LIGO, which is quite instructive and surprising. And this is the way you should think about squeezing in interferometers if you want to mystify people, okay? And part of our job in physics is to mystify people so they think that what we're doing is important. I know that many times we have the opposite point of view, that the point is to explain things clearly to people, but they're not gonna understand it anyway. So why not mystify them a little? All right. And I know this for a fact because I hear my colleagues mystifying people when I could have done a better job of explaining it anyway. All right, so what LIGO is basically is a Fabry-Perot-Michelson interferometer with power recycling. So here we see the laser, and here we see the laser, which is producing light. There's the recycling mirror. Here are the cavities in the arm. And what the laser does is it excites the symmetric mode of oscillation of the two cavities. And if you think they're not actually in phase, I'm defining that to be the symmetric mode. So the two, this is a test of whether I'm still coordinated, which I'm not. Anyway, the electric fields in the two arms are in phase, going up and they're oscillating in phase. Now, if we put light in from the antisymmetric port or the unused port, or what's often called the vacuum port, which is the one where we need to put the squeezing. If we put light in there, that excites the antisymmetric mode of oscillation of the two cavities, where they oscillate 180 degrees out of phase. What a signal does, so what the laser does is to excite the two cavities into this enormous mean field state, oscillating in phase in the symmetric mode. What a motion of the mirrors does, so the gravity wave pulls out this mirror and pushes that one in an oscillatory fashion. And that produces and what that does is cause a transition from the symmetric mode into the antisymmetric mode of oscillation. A tiny amount of light goes into the antisymmetric mode. And when that comes out, it comes back in this direction. And that's the gravity wave signal, okay? And what we just said was the shot noise works the same way. The shot noise fluctuations come in from the antisymmetric port and come back down through the antisymmetric port. That's a way of saying how the whole thing works without having to go through those little diddly arrow diagrams. If you believe in modes, this is the way the thing works. So, in a LIGO, probably just before the current observing, I don't think these figures have changed much because they really are pretty close to the limit of how much power they can produce. They're out of gas on that. And that's why they had to use the squeezing. They had to finally do what I told them anyway. But that's why quantum metrology is hard. It is always easier to produce classical improvements for your device than it is to use these quantum techniques. And until your back is against the wall and nothing else works, and you will not use quantum techniques. But their back was against the wall. Thank God. Anyway, they have a laser that produces about 20 to 30 watts of power. Inside the recycling mirror that is incident on the beam splitter is something like 700 watts to a kilowatt. And the circulating power in here is truly alarming. At the time, it was 100 to 150 kilowatts. Design was 1 megawatt, which means they didn't get to their design power. I think it's up now to 700 watts, 700 kilowatts, which is pretty darn impressive. I mean, you don't want to be in that vacuum standing in the way. Anyway. So, what would they have to do? Let's see what I wanted to say next. Yeah, so this is about 4 times 10 to the 18 photons per millisecond on the beam splitter. I think that's up a bit, maybe to 10 to 19, maybe a little higher than 10 to 19 photons per millisecond. What would they have to do to get a factor of 3 improvement in shot noise sensitivity? They'd have to up the power by a factor of 10. So go to 4 times 10 to the 19 photons per millisecond. No, I think these things are about right because they tend to give things in photons per second. Anyway, I think this is more or less right. To produce the same 3 dB squeezing improvement with squeezing, you have to put 2.5 squeezed photons in there. So those are miraculous photons. Instead of putting in another 10 to the 19 photons per millisecond, you put in 2.5 squeezed photons per millisecond, and you don't even want to put them in. They're only photons because of this anti-squeezed quadrature. And you just prefer that wasn't there. But the uncertainty principle requires it. So this 2.5 miraculous squeezed photons per second is as good as upping the power by a factor of 10. Remarkable thing. So that's the mystifying way to explain it. These are magical photons, these squeezed photons, absolutely magical. All right. So now let's move on. I'm doing better, Anil, than I did at your place with my, what you call it, my, yes.
I was a little confused with this way of understanding. Here, they're like 10 to the power 9, like shot noise photons also. So what happens? Like they'll basically not see this difference, right?
They'll basically not see the.
Because the laser is also carrying.
Yeah, but any fluctuation. Oh God, how did Ron get up there? any fluctuations from the laser, if the thing is, so they're operating on a null in this direction, or very close to a null. Actually, they don't quite operate there now. They operate a little bit off and use a little bit of mean field from the laser to do homodine detection. But they're essentially operating on a null. So anything that comes from the laser, if the thing's properly balanced, goes back to the laser. So any laser fluctuations are totally irrelevant. And that's why they have the recycling mirror there, because 99% of the light comes back out in this direction and they just put it back in, which means they have cavities inside of a big cavity. And all of that has to be stabilized and locked up so that you can get any light into it all. Because these are cavities that are pretty amazing with, well, as you know, incredibly narrow bandwidths. The relevant thing, and even that little trivial calculation I did at the beginning, the relevant thing is the number of photons incident on the beam splitter from the laser. That's what sets the mean field, and it's the size of the mean field that determines the size of the shot noise. It's not actually the number of photons that come out in this direction, which is technically zero if they're on a null fringe. All right, so again, that's the miracle of an interferometer. But it is that power, the one that's instant on the beam splitter, that's important. Yeah.
So the squeezing plays no role on the back action?
You're asking about the back action?
Yeah. But it shows the curve where everything seems to
Yeah. So the thing is, if we put squeeze light in here with the phase quadrature squeezed, then the amplitude quadrature will be unsqueezed and it will rattle these mirrors around. But that will then appear in the signal quadrature at the output. So the noise at the output will be a combination of the phase quadrature at the input and the amplitude quadrature at the input. And what Unruh suggested, and that's a function of frequency because of the way everything is. I mean, one of those fluctuations is processed through the response function of the mirrors. They're pendulum, basically free masses, and the other one isn't. So that's why at high frequencies, if you just do a little calculation, although I say it's a calculation that nobody did very well for a long time, but if you do a little calculation at frequencies in a current LIGO interferometers above about I think it's about 50 hertz, maybe it's 100, your shot noise limited, and below that your radiation pressure noise limited, and at about 50 hertz the two are equal. So but all of that stuff comes out in the same quadrature at the output. So Unruh's idea was squeeze the thing that actually produces the noise, and that's called frequency dependent squeezing, and that's what's now been done as of this past spring, and as of their announcement. They announced that a week ago Friday. So pretty remarkable. Let's see, okay, I'm in good shape. Terrific. All right, so I just want to emphasize, because this is not necessarily the standard view. What I said was, well, this is a standard view. Why is quantum metrology hard to apply? Because it is almost always cheaper and easier, especially if you have $1 billion, which these guys had, to buy classical improvements in technique. And classical improvements in technique, well, there's one important thing about this. You cannot integrate forever. You must detect the gravity. They want to have broadband sensitivity, so you want to be able to detect the gravity wave while it's there. Whereas in a static situation, you just integrate forever and collect more photons. They can't do that. So the only way to get more photons is to get more. And after a long time, they finally hit a kind of limit on how big their power can currently be. That may change over time, but presently there's instabilities in the system that they're not able to get around and make the power higher. So The person who seeded almost all of that wonderful classical technology to make things better was Ron Drever. And Ron's contributions were put a Fabry-Perot in the arms of the Michelson, so the light is stored for a millisecond, that is roughly the gravity wave period, and you build up the signal as it bounces around inside the cavities. Before that, people wanted to do delay lines, probably hopeless. And it was Ron's fundamental idea, both to propose that and then to make up the technique called Pound-Drever-Hall locking for locking a cavity or the laser to the cavity so you can get the light in and out. And then Ron's next idea was nested cavities, which is recycling, which here I've just talked about signal recycling, and that is absolutely crucial. That jacks up the power, as you saw, by a huge factor, power on the beam splitter, and without that, nothing would be detected. As one of my good friends who was a postdoc with Ron in the early 80s said after hearing, this is Dana Anderson at Jilla, Dana said after listening to a LIGO colloquium, he said, you could take their optical design and find it in one of Ron's lab notebooks from 1984. All right, and then there is, I do regret, I mean, I have to advertise myself. So I'm the one that proposed the squeeze light interferometry, and then there's over time that's been elaborated to what they now do with the Unruh technique. What is that picture? When Kip won the Nobel Prize, he said, "Carl, I want a picture of you to show it in my Nobel lecture." So I sent him a picture of me, and he said, "I don't want a picture of how you look now. I want a picture of how you look then." And so I went and found this one, and that is the motivation for my current hairstyle, although I can't get my hairstylist to let it go quite that long. The other motivation is, I mean, I hate to say this because these people that this would be aimed at in the audience. If you're 72 and you've got hair, flaunt it. All right. So Ron's classical ideas ran out of gas after 35 years, and this is what I said in 1981. So experimenters might then now be forced to learn how to very gently squeeze the vacuum before it can contaminate the light in their interferometers. Bit of a regrettable split infinitive there, but my excuse is that nobody even knows what a split infinitive is now. And besides, if you know what you're doing, you can do it. Boldly go where no one has gone before. You can do it if you know what you're doing, but if you don't, try to avoid it. All right. Oh, let's take a break. And now we'll get on to the second. So that was the story. The story is the story of Gaussian noise going into an interferometer and how you can manipulate it using nonlinear optics to produce squeeze light and therefore improve sensitivity. So there's a noise model, and there are known ways with nonlinearities to produce squeeze light. And so over 40 years, people had an incredible set of ideas of how to improve sensitivity. And now we're kind of at the point where what can be done has been done. And these techniques of squeezing will be in every gravity wave interferometer, Earth-based, from now till the end of time. All right. Now I want to look at a different way of thinking about the limits on optical interferometry. And that's going to involve introducing some concepts, which I'll talk further about tomorrow. And now we're in the side where you get proofs. And I'm going to show you how you prove something. Today I'm not going to show you how you really prove something. I'll show you that tomorrow. But today I'll show you the elements of a proof. And when anybody says that, they're going to show you the elements of a proof, you should not believe them. But in this case, you should. All right. So we saw that the shot noise limit was this. sensitivity for detecting a phase shift in the interferometer goes as 1 over the square root of n, that's the shot noise, times the uncertainty in the phase quadrature coming in the unused port. All right, for a coherent state coming in the unused port, both the amplitude and phase quadratures have the same uncertainty, and so we genuinely do get the shot noise limit, 1 over the square root of n. We could, however, think about the following. Let's say we squeezed enough that the squeezing was like this. That is, the anti-squeeze quadrature had as many photons in it as the mean field. And what that means is in the arms, the squeeze light looks like this, where the squeezing, there's the mean field, the squeezing goes right down close to the origin. If you squeezed any more, the phase would start to get uncertain by a factor of pi, right? So if you just say, okay, I want to squeeze that much, then you will have these formulas for the quadrature uncertainties, and the phase uncertainty will go as 1 over 2n, and that's called the Heisenberg limit. So good question is, when do these limits hold? When are you stuck with shot noise? And when can you get to the Heisenberg limit? And do we think these are limits only because we haven't thought hard enough, right? Because we're thinking in terms of a very specific model of the way the noise runs around in an interferometer. And maybe that's a restriction on our thinking. So we should think more generally and try to prove something about what's the best sensitivity we could get. So that's what we're going to now do. So I do want to emphasize something. Given the enormous number of photons in LIGO, photons per millisecond in LIGO, there's no way the Heisenberg limit is of the slightest relevance. It would mean that you had you'd have squeezing that had 4 times 10 to the 18 photons per millisecond. The improvement in sensitivity would be about 10 to the 9, and that ain't gonna happen. That ain't gonna happen. But maybe in other contexts, that could be made to happen, and you might get to the Heisenberg limit. Again, typically, anytime you see people using quantum metrology to improve sensitivity, they could have gotten the same improvement by just making their whole system better and using classical techniques. So they've made a crummy system on which they have then used quantum techniques to make it better. But you know, that's important. It's important to demonstrate that the quantum techniques actually work. And you're not going to demonstrate that unless you are able to use them, okay? All right. So a very important concept in what we're going to be doing now is called the Fisher information. And the Fisher information is based on a very simple set of ideas. And it's important to understand this because once you get into the Fisher information, it seems so counterintuitive that you wonder what the heck it's about. So here's what the Fisher information is based on. Let's say we are estimating a probability P from n trials. And so we could think of that as a random walk where we have a probability P for a step to the right and a probability 1 minus P for a step to the left. Or we could think of it as just polling. We have 2 candidates and there's a probability P that people prefer candidate 1 and a 1 minus P for probability 2. And we want to estimate that probability P. So the way we estimate that is in n trials, we define the frequency, which is the number of times the P probability comes up, divided by n. The mean value of that is just P, and the variance of that is PQ over n, where Q is 1 minus P. All right? So let's say we measure the distance between neighboring probability distributions in units of their distinguishability. So we will have 2 probability distributions that differ in P by delta P, and we're going to measure delta P in units of the variance in the frequency. actually the uncertainty in the frequency. So we put that in, we just do a little screwing around. There's an important step here, which is to separate this thing into two parts. And there it is. That is the Fisher information. Sorry?
The second term is also delta P. Second term.
Yeah, it involves delta Q squared, but delta Q is equal to delta P with a sign change.
Okay.
So that, you have to realize you should do that. That won't be true if we have more than two alternatives. But in this case, it's trivial. Delta P and delta Q are the same. That's the way we managed to separate these two guys out. So this measure of measuring the difference between two probability distributions in terms of the variance, in terms of their statistical distinguishability, in terms of a frequency, gives us this kind of metric on the space of probability distributions, which is called the Fisher information. All right. It's important to see it's delta P squared over P plus delta Q squared over Q. That's the way it will always appear. And there's something important in that. It's not, for example, this, or this, or this. It is specifically this. And that's important. That's a metric on the space of probability distributions, and that probability distribution, that space of probability distributions in this case is just a line. So here's P and his Q, P plus Q is equal to 1, so it's just a line. And this is a metric on that line, okay? And what I'm about to say is completely general. If we go to coordinates that are the square roots of the probabilities, then just becomes the Euclidean metric. So in terms of U and V, the probabilities are on a piece of a circle. Generally, they'd be on a piece of a sphere. And the Fisher information is just the induced metric from the surrounding Euclidean space. That is, you look at it and you can see the difference. Okay, you cannot look at this and find the difference between two nearby distributions from the flat space in which it's sitting. Here you can do that. It's a very handy way of thinking about what the Fisher information actually means. Because it means that over here where either P or Q is close to 1, if we take a little difference between P and Q, there's quite a big difference between them. So when distributions are close to 1, it's very easy to distinguish them. There is a kind of caveat in that I'm not going to go into, but it's very easy to distinguish two distributions that are very close to 1. Okay. So here's the general formulation of that. If we have a parameter phi that affects a probability distribution pj of phi, so J runs, let's say, from 1 to n. It's the set of different probability of J given phi. As phi changes, the probability for each of the J's changes. And the Fisher bound is this. If we choose any estimator for phi, from any data that we collect, the uncertainty in phi, the estimator, is 1 over the square root of n times 1 over the square root of the Fisher. And the Fisher generally is what we had before. It's delta P squared over P. And the derivative here is because really the d phi squared should be over here, multiplying the Fisher as it is here. So that is a kind of zero order derivation of what the Fisher information is. We're going to see the rigorous derivation tomorrow, but what we're going to show you now is how we apply this in quantum mechanics. All right, so we're going to have a quantum information version of interferometry. Looks entirely different from an interferometer. And that, of course, is the power of doing theoretical physics. We have pictures which we've abstracted away from the real world, and the pictures look entirely different from the real world. You just have to have an internal map in your mind of how to get the pictures connected to the real world. And the talent in doing theoretical physics is mapping the pictures to the equations to the real world and carrying that around in your head so that when you see a diagram like this, you say, oh yeah, that's an interferometer. That's an interferometer. And you don't even have to think about it. That's what a theoretical physicist does, okay? I don't want to say what experimental physicists do. And I'll tell you a story. Ron Drever, the person I referred to there, I probably had dinner with Ron 1,000 times between 79 and 84. And the guy was a genius, but he couldn't add 2 + 2. He'd just sit there. He skipped the equations. He had a direct connection from little pictures that he drew to the real world. And he'd show you the little pictures and say, this is what you should do. And you'd say, geez, I don't know, what are you talking about? And then you'd go off and look at it. Yeah, that's what you should be doing. So that's why I don't want to say how experimenters are thinking, because I know Ron was a genius. Well, what Ron taught me is you don't have to be Kip Thorne to be a genius in physics. You can be totally different from Kip Thorne. All right. So what we're going to imagine is we have either photons with 2 modes or atoms with 2 levels, and 0 is one of the modes. That could be the stuff going into the interferometer from the laser, and the other mode is the stuff coming from the other port. Or atoms, it would be ground and excited level. So 0 might be ground and 1 might be excited level. And then those are subjected to some kind of, those are subjected to what we call the Hadamard gate, which just mixes 0 and 1 equally, just like a beam splitter does, okay? And then those are subjected to each photon is subjected to a rotation. Z is the Pauli Z operator, you don't have to worry about that. So there's a rotation, and that's the phase shifting in the arms of the interferometer, or for an atomic system, it's rotating between the ground and excited state in the qubit fashion. And then there's another set of beam splitters called the Hadamard gate, and then we make a measurement, and we get, in this case, we'd get what's called the quantum noise limit, which is the shot noise limit. Okay, so that's our picture. So here's what you'd imagine sticking in 0. The Hadamard gives you an equal superposition of 0 and 1. The phase shifter does this. The Hadamard gate then translates this phase shifts to amplitude. Again, that's what an interferometer does, is take phase shifts and turn them into amplitude. So the amplitude for 0 and 1 varies sinusoidally with phi. And so there's your interferometer, and that one will have what's called what I now call the quantum noise limit. It's the shot noise limit, okay? And the Heisenberg limit is obtained in the following way. We put in the same zeros. We beam split one of them, and then we do these things called controlled knots, which flip this if this was in 0. Don't flip it if it's in 0, but flip it if it does. So after the first Hadamard, you get this 0 + 1, and then after the other 2, you get a so-called cat state, which is 0, 0, 0 + 1, 1, 1, because when this guy's 1, it flips these 2, okay? And there we are. We then do the phase shifts. The key thing is now these phase shifts are n times as big as they were before, because all these guys are in 0 and all these guys are in 1. And then we reverse all that, and we get this deal here where the first we get this state here where the first of the qubits is in 0 with this amplitude and 1 with this amplitude, and the phases run n times as fast as usual, so you get a sensitivity that's n times bigger, and if you just work through that, that gives you the Heisenberg limit. Okay, so the key thing there is, I sort of forgot, we get a fringe pattern with period 2 pi over n, so instead of the fringe pattern running like this, it runs like this, and if you sit at the right point on it, there's a very steep change in phase for a tiny very steep change in amplitude for a tiny change in phase, and that's how you get to the Heisenberg limit here. All right, so there's the whole deal in circuits, and now we're going to prove something. So that was for an interferometer, which we just repeated there. And now we're going to, in the typical theoretical physics fashion, we're just going to label everything completely generally and hope that we can prove something. Okay? So single parameter estimation is the following problem. We start in a standard state. We have a arbitrary unitary across the entire unitary operator across the entire set of inputs. We then impose our phases. These are all the same Hamiltonian. We then have another arbitrary unitary, which could involve an ancilla, which wasn't involved with the signal. It won't make any difference. And then we make measurements on everything. So the way we describe that is that first unitary is state preparation. Here's the dynamics, or the position of the signal. And then here's the measurement. Okay. And you can see this is a generalization of what's above. So if we can prove something about this, it applies to that thing up there. And here's what we can do. Now I'm looking at a particular kind of proof of this that many people have proved this over the years, but the particular way this is formulated is from this paper by Giovannetti, Lloyd, and McCone, which all the rest of us just used, which we used in this paper. And what I'm repeating is what we did in this paper. All right, so there's that same circuit. The dynamics is by a Hamiltonian, which is the sum of all the individual Hamiltonians. And then what you can prove is that there is a quantum Kramer-Rao bound, and this is what we'll prove tomorrow. There is a quantum Kramer-Rao bound, which can be regarded as a generalized uncertainty principle, which says the following. No matter what your measurements are, you take the data from those measurements and you construct an estimator of the signal phi. You can do that any way you want. It doesn't matter how you do it. It's always true that the uncertainty in that estimator is greater than or equal to 1/2 times 1 over the uncertainty in this Hamiltonian at this point in the circuit after the state preparation. So you can see this is kind of an uncertainty principle. H is conjugate to phi, although phi is a parameter. So delta phi times delta H is greater than or equal to 1/2. It's the right kind of uncertainty principle. People will often say, oh, this is not a right kind of uncertainty principle because phi isn't an operator. Well, terrific. What does your operator mean? Nothing. This is the thing you measured, and it is a number, and you have the uncertainty in it. And its uncertainty, no matter what you do, is limited by 1 over the uncertainty, 1 over the quantum uncertainty in the Hamiltonian. Okay? So now you piddle around and you say, oh, terrific, terrific. I will just say that of these systems, H has a biggest eigenvalue, capital lambda, and a smallest eigenvalue, little lambda, and the uncertainty in this Hamiltonian is bounded by, this is all the little h's, have a biggest eigenvalue, big lambda, and a smallest eigenvalue, little lambda, and the uncertainty in H is n times that difference. And how do we know that? You make the uncertainty in H biggest by putting yourself in a state that's a superposition of the biggest eigenvalue and the smallest eigenvalue with equal weights. And then the difference between those things is as big as possible. Okay?
Sorry.
So that's this statement here. Yeah, there was a question.
Shouldn't it have been root n? I mean, aren't they independent sort of?
No, this has no root n in it because we'll have a root n in it in a minute. But every one of these guys contributes the same because they're not correlated at all, right? These Hamiltonians are just separate Hamiltonians for each system. So they just add up, and the total uncertainty grows as n, and it's proportional to this eigenvalue difference. Of course, it is this proportionality to n that's crucial, because you can see that's what gives us the Heisenberg limit. Just a second. For product inputs, oh, sorry. So I probably gave a misimpression. So let me go back and give the correct impression. You are not, what we're going to see is you put all these guys in the highest eigenvalue state and all of these guys in the lowest eigenvalue state, and that's when delta H has this value, and that's a cat state. So it's the same thing we had before. So every system is in either the top state, and that's in superposition, or with every system in the bottom state. So you're quite right. For the cat state, this is true. If you have them in separate states, product states, then it will grow as square root of n, and that's where the quantum noise limit or the shot noise limit comes from. Okay, from this perspective. Now there was a question over there, although I might have answered it.
Yeah, and what happens to this when if the eigenvalues are not bounded?
Ah, well, that's a good question, and it is a sore point. The Fisher information can often screw up when you have unbounded eigenvalue spectrum. So in an interferometer, we're considering an interferometer with a fixed number of photons in it. We're not considering one where the number of photons can vary, okay? And if you do, then you run into the fact that the Fisher will report the wrong answer, sort of. And you'll have to go off and do a much more complicated calculation.
In presence of losses, for example, also. Like,
sorry?
In presence of losses also, how this it's?
I didn't quite.
In presence of photon losses and so on. Like, or...
Oh, I'll say a little bit about losses in a minute. Yeah. Because obviously, it's probably true that everybody can see that losses are going to make that bound, the Heisenberg bound, pointless. All right. So there's our system. You achieve the Heisenberg limit by using a cat state. So you just say, whatever this is and whatever V is, it produces this state. That is a superposition of everybody in lambda and everybody in little lambda. You impose the phases, which is do these guys like this. Again, you get phases that are n times, that run as n times the phase on each one. And then you just say whatever measurement, whatever W does, it converts this, this phase information to amplitude information. Again, you get a fringe pattern that runs n times as fast. And so you get a sensitivity that looks like this. That's the Heisenberg limit. Okay. So I think my time is running out. Unfortunately, also the talk is running out. What we do in real life is for an optical interferometer powered by a laser with a fractional photon loss 1 minus eta equal epsilon, the optimal strategy is to put squeeze light into the vacuum port with ultimate sensitivity having shot noise scaling. And basically, this is the amount of squeezing. This kind of bound in the presence of losses has been shown for all kinds of systems and sort of generally by all sorts of people. And it's a rule of thumb established by many researchers under many circumstances. Reaching the Heisenberg limit requires epsilon times n be approximately 1, or actually less than 1, which is simply the statement that you lose less than 1 photon. So the Heisenberg limit is terribly sensitive to losses. So if you had 1,000 photons, if you lost even 1, the Heisenberg limit is gone. It's gone. There are other states that are more robust against photon losses, but all of them tend to have this rule of thumb as the ultimate sensitivity in the presence of losses. Now, there's one thing I can't help but mention here because I did spend a huge part of my life on it. This group of people over many years applied the quantum Kramer-Rao bound to curved spacetimes and quantum fields running around on curved spacetimes using quantum fields to sense changes in the curved spacetime background. There's a lot of technical difficulties in that. A lot of technical difficulties in that, which were mainly handled by Jim Van Meter. And if you go through all of that, you will find that the sensitivity to detecting a gravitational wave of any sort in linear gravitational wave is given by this, where X1 is the wideband quadrature component that is out of phase with the mean field of the electromagnetic field sitting on top of your spacetime. So that's the field, the quantum field on top of your spacetime. So it's exactly what you would expect, and it's terrific. It says you should use squeezing, and it's a very general sort of bound done in a totally different way than people usually do this. Let's now get to the point. Telling stories is, I think, what physics is all about. That is having models and noise models and calculating what they do. The squeeze light narrative is about understanding fringe patterns and sources of noise and designing devices to improve phase sensitivity based on this understanding. This is all telling stories. Mathematical stories, but still stories. The quantum Kramer-Rao bound is misleading and clueless on practicality, but it verifies whether the stories, always of limited validity, are fooling us. And why is it clueless? The quantum Kramer-Rao bound, if you look at it, it says to make something very noisy. That's what it says. It says make delta H as big as possible, make it as noisy as possible. It does tell you, but you have to know what you're doing to find it. It does tell you what you should measure to take advantage of that big uncertainty in H. But if you just look at it, it says, okay, make something very noisy. Well, you say, I can make all kinds of stuff very noisy, but the bound doesn't apply unless you're in a pure state. So ordinary classical noise won't get you to that, obviously. Okay, so which is better, stories or proofs? Well, I'm a theoretical physicist. You need both. But to design devices, you need a story. All right, thank you. Oh, and I've probably got the last. All right. And I didn't take up all the time that you said I would have.
Hello.
Question.
I have one.
Do you have a question?
Yeah.
Ask it, and then we'll.
In your interferometer sample, show that the noise that comes. Oh, thank you. In your interferometer example, you showed that the noise that enters the unused port of the interferometer gives some troubles. Let's say it like this. Is there any possibility not to use vacuum state, but any tailored state to?
Yeah, so you can put a
do
squeeze
this?
state there. That's the, you put a squeeze state there and that makes things better. Okay. Yeah, that's what you do.
Yeah, so I have one question. The quantum interferometer, quantum version of the interferometer you showed, it uses qubits, right? So, but photons are not qubits, right? So how do you map qubits to the actual interferometer?
Yeah, it's saying that every photon, which is not quite the, so I'll explain why it's not quite the right thing to be doing. Every photon that goes into the interferometer can be in two states, either this arm or this arm. Once you go past the beam splitter, either this arm or this arm. So those are the two states that every photon can have. The problem with using photons as opposed to modes is that the Hilbert space for the electromagnetic field is a tensor product of modal Hilbert spaces. It is not a tensor product of photon Hilbert spaces. So if somebody tells you, draws you that kind of picture, you have to ask the question, what are you talking about? And what you're talking about is, in this case, as I said, you have n photons and your Hilbert space is every photon can be either going in this direction or this direction. And that's a perfectly well-defined Hilbert space, but it's not the most general Hilbert space for the electromagnetic field.
I have a question. In that here. Hi.
Oh,
yeah. So in that circuit that you showed for the interferometer quantum circuit, there you used ancilla probably to realize, I think, generalized measurement on that 3 qubits instead of a projective measurement. But why are we needing that here?
why did I?
That ancilla.
Yeah, why did I put it in there?
Yeah, I mean, what is the?
You could regard it's really for doing one of two things. You could say it's part of the measurement process. That is part of the measurement process is to take the main systems and feed information to the ancillas and actually measure them. That won't make any difference. Actually, the thing is more general than what I said. You could have the ancillas interacting with the other systems at all times in the process and doing feedback and control that is actually actively making measurements while the process is going on, and it still would make no difference. The Kramer-Rao bound still holds. That's what I'll show tomorrow.
Okay. And another is that cat state, which is actually creating entanglement between the first 3 qubits or first n qubits, GIZ kind of entanglement. But what if we create other class of entanglement, W, or does that make a difference?
Yeah, it's one of the reasons I don't think entanglement is one of the world's greatest concepts when it comes to quantum metrology. I don't even think it's very relevant. That is the optimal state. All the other entangled states, they're not as good.
Thanks.
So no measure of entanglement. That one has one bit of one E bit of entanglement, and states that have tons more aren't as good because the measure is the Fisher information. It's not entangled.
Yeah, I have a. Yeah, so this is regarding the Heisenberg limit in that statement.
You what?
This is regarding the Heisenberg limit that you showed, that 1/n. So, so naively, like somehow the quantum advantage for computation and so on seems to be like parallel processing when a single thing is being estimated simultaneously. So from that intuition, one would have expected that if one tries to be clever and designs a unitary, which actually simultaneously goes over like n phi, one would have done better. But your limit seems to be just based on the input preparation. So can you give some intuition of how to think of it, or like why doing something later in the unitary part will not help the limit?
Yeah, well, it's certainly true that the entanglement of the cat state allows everything to run in parallel, but the effect appears to be, as far as the Kramer-Rao bound is concerned, entirely that you make the phase run n times as fast. That's the entire effect, and there's nothing better you can do. That's just it.
There's a product state, but a nonlinear.
Oh, you want to talk about nonlinear Hamiltonians?
Which combines. And what happens?
Yeah.
Really going out of time. Maybe so. So there's one more last question by student.
I think you're going to hear about that from one of the other speakers.
So I just wanted to know that you said that people usually don't, you talked about generalized uncertainty relation. Generalized uncertainty relation, where delta phi was there. And then the phi is not treated as an operator. The phase is not treated as an operator in quantum mechanics. Is it because it's a conjugate to like the other this thing that is time, which is also not taken as an operator in quantum mechanics? I just wanted to know what is your take on the time as in like in quantum mechanics?
The thing that people think of as the classic uncertainty principle in quantum mechanics is the Robertson uncertainty principle, which is a consequence of the Fourier transform for X and P, or more generally, other kinds of Fourier structures for, let's say, JX, JY, and JZ. And those are wonderful uncertainty principles, but they simply say that in any state that you can imagine, the uncertainty in X times the uncertainty in P is greater than or equal to H bar over 2. And they don't say how well you can measure anything. They have, intrinsically, they say nothing about how you can measure anything. This directly says how well you can measure something, a parameter that is imposed on the system. And energy time, yeah, the only reliable energy time uncertainty principles are Kramer outbounds. I mean, those started to be devised in the 60s, and they amount to being exactly the same as Kramer outbounds.
Okay, so I request the further discussions can happen during the break time. So let's thank Professor Carlton once again.